Picture this. It's late at night, a factory floor, totally silent except for this one low hum. A massive robotic arm sits there, completely motionless, and then, without a single human in sight, it stirs. It starts to move, and not just, clunky machine-like movements. It moves with this grace, this precision that seems, it seems impossible for a hunk of metal. It's a perfect fluid dance of steel and wires. It's almost alive. But you're looking around, right? There's no one there. No puppeteer, no visible strings. So, what is it? What is this digital ghost that's taking a single line of code from a computer and turning it into this intricate physical ballet? Okay, so let's pull back the curtain. That ghost in the machine, it's actually a super powerful software framework called ROS2 Control. You can think of it as the central nervous system for modern robots. It's that invisible bridge between a simple idea and a physical action. And this is our map. I know, it might look a little complicated at first glance, but trust me, this is the key to our whole mystery. This is the journey we're about to take, and we're going to keep coming back to this map as we uncover each piece of the puzzle together. So what we're going to do is trace the path of one single command, right from the very top, all the way down to the metal, to the physical hardware. We're going to see exactly how a robot truly comes to life. All right, every good story starts at the beginning, and for us, that's the foundation, the hardware itself. You can think of this as the robot's muscles and its senses. We're talking motors, joints, the sensors that let it feel the world. This is where all those digital commands finally become real, physical movement.
When this framework looks at a robot, it doesn't just see one big thing. It breaks it down into three types of parts. You've got your big, complex systems, like a whole industrial arm. Then you've got sensors, which are basically its eyes and ears. And finally, you have the simple actuators. Those are the individual motors that move just one joint at a time.
Okay, let's move one level up on our map. Here, we meet the gatekeeper. And I mean that literally. This is the resource manager, and its entire job is to control who gets access to that precious hardware.
Just think about it for a second. What would happen if two different parts of the code tried to move the same exact joint at the same exact time? It would be total chaos, right? The robot could literally tear itself apart. Well, the resource manager is like a strict bouncer at a nightclub. It makes sure only one command gets through at a time, preventing that chaos. It is an absolutely crucial layer of control.
All right, let's keep climbing up that chain. So, above our bouncer, our gatekeeper, we have someone even more important, the orchestra conductor. This is the controller manager, and it's basically the main entrance for any command you want to send. Now, what's really interesting is the controller manager doesn't actually move the robot itself. Nope. Instead, its job is to decide who gets to move the robot. It's like a project manager, dynamically bringing in different specialists. We call them controllers for whatever task is at hand. It really is the brains of the whole operation. And that brings us to the very top of our map, the controllers themselves. So if the controller manager is the conductor, then these guys are the specialist musicians in the orchestra. Each one is a virtuoso. They know how to play one instrument, or in our case, control one very specific type of motion, perfectly. So there you have it. That's the system in a nutshell. Now, let's really put it to the test. Let's trace one command through this entire chain and watch how a simple idea becomes a physical action. Okay, theory is one thing, but seeing is believing, right? Let's see this ghost in action. We're going to use a simple, simulated robot with just two joints, and we're going to give it a direct command. And this is it. This one line of code is our message to the machine. Now, don't let the text scare you. It's actually super simple. All it's saying is, hey, robot, move your first joint to a position of 3 radians. And a radian is just a way to measure angles, kind of like degrees. Then it says, and just leave that second joint alone at 0. That's it. Incredibly simple, isn't it?
And bam! Look at that. It's a perfect illustration of the result. On the left, the robot is just sitting there. We send that one single command, and instantly, on the right, it snaps to attention and moves exactly as we told it to. The ghost is real, people, and it works flawlessly. But what if the pre-written music isn't enough? What happens when the standard moves just won't cut it? What if we want our robot to do something completely new, something that's never been programmed before? What if we want to teach it to dance a new dance?
And this is where the true power, the real magic of ROS2 Control shines. See, it's a modular framework. That means if you need a totally new kind of movement, you don't have to tear everything down and start over. No way! You just write a new, custom controller and plug it right in.
So let's compare these two ideas, because this is really interesting. That pre-built controller we just used, it just forwards a command. It's basically a mail carrier. It takes a letter and delivers it. But a custom controller, like this sign controller we're talking about, is totally different. It actually creates the command. It's not the mail carrier, it's the person writing the letter, implementing a brand new rule for motion completely from scratch.
And would you look at that? That's the result. By just activating our new custom controller, the robot is now performing this beautiful, smooth, continuous cyclical motion. It's a perfect sine wave. We taught the digital ghost a new trick. We gave it a brand new dance, just by plugging in one new piece.
And I want to be clear, this isn't just some neat simulation trick. This modularity, this ability to plug and play, this is exactly why frameworks like ROS2 Control are so fundamental to all of modern robotics. It lets developers build up incredibly complex behaviors out of small, simple, reusable parts.
So let's go back to our map one last time. It's not a mystery anymore, is it? We can see the whole story. From top to bottom, a command comes in, the conductor, the controller manager, picks its specialist musician. That musician asks the bouncer for permission to use an instrument, and it controls the physical hardware to create motion. It's a beautiful, elegant system, and it all works in perfect concert.
And this isn't just theory. This is happening in real robots all over the world right now. Take a look at the TIAGo robot. It uses one controller to drive its base, a totally different one for its arm, another for its gripper, and even more for its head. And all of it, every single piece, is managed by the same ROS2 Control framework. It really is an orchestra of specialists, all working in perfect harmony.
So, we've done it. We've unmasked the ghost. We now understand that low-level nervous system that lets a robot turn a line of code into actual physical motion. But this just opens up an even bigger, more fascinating question, doesn't it? We've seen how robots move, but how do they decide? How do they choose what to do next? Well, that's a story for next time. Hari ha.